Well, thanks, and welcome to. Oh, I thought that was a silent. Welcome to our boot camp, and I was tasked to give some introductory talk and trying to get people all on the same page. And I really want to thank all the other speakers who have agreed to come. And as Alistair said, I think the talk will be boring to the experts, and I apologize in advance. And I really try to hopefully make it elementary and understandable, and interrupt me any time you would like. And so this is going to be actually one of the several, I think we plan on 3, I'll give 2, and Hung will give the 3rd on the classification program. And in fact, Shi Chen will give some other talks that very much relate to this. And what I like to basically bring everyone sort of to get a sense of what this is all about is that, we're looking at problems, but not necessarily individual problems. Of course, we're interested in individual problems, but the program is much more looking at the class of problems and try to get a dictionary of sort, right? It's sort of like a chemist, here's the element table. You try to lay out that. In some sense, this is perhaps the ultimate goal for complexity theory. You try to classify everything you can. We're going to focus on sum of product type computations for this aim for dichotomy theorems, which try to classify everything in a class. And they tend to be sort of sum of product computations that have been mostly successful. And in fact, we'll have 3 frameworks to discuss this. And they are very much related. Here are the 3. The first goes by spin systems, or graph homomorphisms, or weighted graph homomorphism partition functions. And we'll come to that when we introduce slowly. But basically speaking, say you have a set of points, and they have neighboring interactions. And the points can assume, let's say, up or down valuations. And depending on if they're both up and up, or down, down, or up and down, and down, up, if it's directed graph, there are only 3 possibilities. Undirected graph, 3 possibilities. Then you give some sort of value, a weight. And then you multiply these weights together as the total weight, and you sum over all the assignments. In statistical physics, they sum the weights, and then you put on the exponent, which is really the same, e to the sum, and then you have some parameters in front. There's at least almost a different view, but it's really essentially the same of what's called graph homomorphisms, which has a longer tradition in, or at least has a long tradition in combinatorics. We'll come to that. CSP, everybody probably understands. You have a set of variables that can take values in some finite domain. And then you have a set of constraint functions which can be used to apply on various subsets of functions. Actually, subsequences of functions, because they might be order dependent. And then you consider all the assignments to the variable, and you multiply the evaluations of the function. The function, if it's 0, 1, then it's just a satisfaction, sort of, if it's all satisfied or not. And then you sum over possible assignments. Okay, so the spin system can be viewed as a special case of the CSP where you have a single binary function on the edge. And then we'll talk about this framework called Holland, which is a generalization of CSP, where, say, for example, perfect matching is one of those problems where you assign values to the edges if you pick the edge or you don't pick the edge. And you, at the vertex, you say, I have the constraint, which is exactly one edge was picked. That's a valid configuration locally for perfect matching. And then you sum over all possible assignments of the subset of edges of 0, 1, and you multiply with 0, 1. That's the counting number of perfect matchings. We'll come to that. Friedman, Lovász, and Squiver showed that you cannot express perfect matching in a spin partition function. This is the strict extension. And reverse, it's obvious. You can do one. You can simulate these guys by this. These things can all be talked on general domain. And if you have variables taking over red and blue and green and yellow, and these are called higher domain questions, and they tend to be more difficult to classify. And my talk here will be focused on the Boolean domain. So you have, that's plenty to work on actually. The variables will take 0, 1. Okay? The values of the function can be arbitrary, really complex numbers. And I like to actually in this talk focus on this newer development of the last 10, 15 years about holographic reductions as both a method of proving hardness as well as discovering new algorithms, and then ultimately as a way to classify problems. Okay. Okay. So I'm actually writing a book, and it's currently in its draft form. It's on my website. You can download, and some of the talks here will be based on some chapters here. For example, today's I think is going to be on the chapter on the match gates. Okay, so let's get going. Everyone knows what the class number P or sharp P is, which is basically the counting version of NP. All right? So everybody knows what NP is. Everybody knows what P is. Everybody knows what Turing machine is. Okay, wait, right, regress here. You know what a Turing machine is. You account for the number of steps a Turing machine takes. And think about non-deterministic Turing machine as sort of at every point you might have a finite number of choices as valid moves. Or you can say a priori I'm given an x and a guess of y of polynomially long, and then depending on the particular y guess, I have a deterministic polynomial time computation. That's NP. Okay? NP says if there is a y that makes it right, makes it accepted. And sharp P is basically defined as how many y's, how many non-deterministic computational paths that will make the acceptance, right? So you think about like satisfiability. Is there a satisfying assignment? That's the NP problem, satisfiability. Number set is how many satisfying assignments are there. Virtually anything you can think about an NP problem, you can think of in a counting version, how many satisfying assignments, and you can even have weighted version. These partition functions are typical things of this sort. You know, sum over exponential and many possibilities, each one of them contributes some sort of weight, and you want to sum them over. As I said, we would like to classify broad classes of counting problems, but before we want to sort of assume that we can classify, we should at least acquaint ourselves with something that are actually computable. I mean, you should know, I guess that the whole philosophy is that P is not equal to sharp P. Okay, this is an assumption that everybody, I think, mostly agree. At least it's implied by NP not equal to P. If you think P equal to sharp P, then this classification program becomes not very interesting because everything is in P. But nevertheless, these theorems that are proved here do not assume that. And in fact, if you once had the classification, then you can prove anything that is considered the sharp P hard in the classification to prove it in P, then it will solve your problem, which is P equal to sharp P. So let's just assume that P is not equal to sharp P. We would like to classify, and therefore we would like to have at least some understanding of things that are doable in polynomial time. Okay? So there are decision problems versus the counting problems. Sometimes the decisions are easy, but the countings are hard. But more pertinent to us is that actually there are some sharp P hard problems that are in general, for example, perfect matching, counting number perfect matching. But it is actually solvable in polynomial time over planar graphs. This is a very non-trivial class of problems that you would like to get at your understanding. Is that clear? Okay. We're trying to get. So this talk is going to be primarily an introduction to the algorithm called the Castellian's algorithm, which computes the number of perfect matchings, or the weighted sum of perfect matchings over planar graphs in polynomial time. And then using that as an engine, as a basic tool to trying to come up with some other algorithms. And then one of the goals of the classification program here eventually will be, and I think maybe Heng will touch today in the third lecture, is to prove that in a very strong sense, these are the universal method, that anything that are generally hard over general graphs to count, hard meaning that it's sharply hard, but becomes polynomial time solvable over planar graphs is doable in this way. Okay, we have theorems that state to the effect that over the broad class of CSP problems, this is universal. But for the Holland problems, turns out that it isn't. And so there are some very surprising additional things that are sharply hard in general graphs, but not, and polynomial time over planar graphs, but are not doable by this transformational universal method. Okay? I mean, if you think about it, the claim of the universality of some one method of this in the class level is rather amazing, because I don't think there is any such thing in, say, decision problems. If somebody tells you this problem can be solved by dynamic programming, if you see it, you know it, but what does it mean by it cannot be solved by dynamic? And there's no real formulation in that sense, that lacking such a formal definition, that much less of any proof of that sort. Okay. So, as I said, this is known as the FKT algorithm, named after Fisher temporally independently and Castellian independently. They actually did independently on the grid first, and then Castellian did on the planar graph. So sometimes it's just called a Castellian algorithm. So formally, mathematically, the planar version is due to Castellian. The proof, anyway. It's the same algorithm. So FKT sometimes called. Okay. In order to introduce that, I would first have to go to Fafian. Okay, and I assume that at least half of you probably know what Fafian is, but let me use Don Knuth's claim that it's more important than determinants. So at least you have every reason to want to know. This is a half sentence. The fact that the Fafians are more fundamental determinants is something to the effect that he said that determinants are basically bipartite special cases of Fafian, which is true. But I'm not sure in the community of algebra community people would believe that determinants are anything second to anything else, right? This is like, but anyway, so you'll see they are very much related anyway. So what is a Fafian? You start with a skew symmetric, so antisymmetric matrix. So let's think we all talk about over complex numbers. So there's no characteristic 2 business to monkey around. And then you look at this matrix, and then there's a matrix function. Okay, it's a value. If the xi's are complex numbers, then the Fafian of this matrix is this polynomial, is this value. Okay. So here's the formal definition. You're given an n by n skew symmetric matrix of even order. The odd orders are defined to be 0. And the Fafian is very much like the determinant. You see, there's a sign over permutations, and then these sort of products of different rows and different columns. But formally, you're summing over permutations that are expressed as this way: 1 to I1, 2 to I2, and so on. Okay. For each permutation, you insist you have this additional constraint. Some definitions don't require that, and there is a multiplier, and then you have to mod out, but we'll come to that in a minute. But let's stick with one definition. So you stick with this particular permutation. Insist that I1 is less than I2. I3 is less than I4. I sub 2k minus 1 is less than I sub 2k. And then I1 is less than I3 and then less than that. Okay. So first test, first quiz for the mornings that to see that you're awake, that I1 is 1 by this constraint. Yes? Okay. Yes? Okay. So this is really saying is that let's pick the smallest I1, 1 here, and let's pick its mate, I2. Okay? And then take the I1, I2 out. The remaining I3 must be the smallest remaining. And you take that, if I2 is not 2, then I3 is 2. If I2 is not 2, then I3 is 2. And if I2 is 2, then I3 is 3. Okay, so it's to pick the smallest. And then you say, what's the mate for I3? In other words, you're looking at the partitions of this n into pairs of disjoint tuples, and you canonically name such a partition. That's what it is. One must belong to one of the pair, and that's the I1. And its mate is called I2. Okay? And then you look at the smallest lexicographic, the smallest pair. That's I3, I4, and so on and so forth. So if you think about the partitioning of n into pairs of disjoint pairs, then there is obvious association with the perfect matchings. Right? So you have n points even, and you somehow try to pair up in a disjoint way. Now, of course, the pairs, if you think about these pairs of points of I1, I2, 1 to up to n as not necessarily as points, but they are not necessarily with edges, then this particular partition will correspond to a perfect matching if and only if every one of those particular pairs is an edge. So the sum is over all potential perfect matchings, and the value, if you think of this as sort of adjacency matrices, then this will give you a non-zero term if and only if it's a perfect matching, but with a sign. Okay, so clear? So that's what the definition of Fafian is. And the sign of a permutation, of course, the ordinary thing in group theory. It's an odd permutation or even permutation. The definition is if you have written down as a product of transpositions, if the even number of transpositions are odd, and that parity is invariant, and that's one of the basic things you prove in groups. All right, as I said, there's a one-to-one correspondence between the Fafian terms and these partitions. And of course, every such partition, for every permutation, whether or not satisfying the stipulation of this ordering business, correspond to such a partition, right? You just pick the first two, the second. But then for every partition, there's a unique way to write down this permutation. Okay. Now, pick such a permutation that not necessarily satisfies this stipulation. You can still define such a term. And because that this matrix is a skew symmetric, that if you switch the I1, I2, or IK plus 1, it changes the sign exactly by 1 for the permutation. And this is a skew symmetric also contributes a negative sign. So therefore, in fact, you can write down this thing for the matrix, and will be the same regardless of what the permutation satisfies the stipulation or not, as long as it belongs to the same partition. So every partition corresponds to, I don't know, some n, k factorial, and then 2 to the k many different ways, right? Exactly one of them is canonical. And every one of those terms corresponds to the same term. So another way of writing the Fafian more like the determinant is the sum of all permutations, and then you divide out by this 2 to the k factorial. Okay? So that's... But it's interesting that I could compute this thing regardless if the pi satisfied the stipulation or not. That's important. Now, there's a sort of a essentially equivalent way of looking at these signs that you can define what's called a crossover. So if you have 4 indices, you list the smaller one before the bigger one, and then you say the red pair and the blue pair had a crossover if they have this sort of a condition. Okay? So this or this. And of course, there's the only other 2 configurations when they are ordered pair, this way or that way. And there they are not crossed over. And this is crossed over. It would be the case if you write down these 4 points on a semicircular point, a curve, and you have And then you have the red here and the blue there. And this is a crossover. And if you order it in such a way that they don't cross over geometrically, that they don't cross over. So it's also a geometric definition. Okay, so now there's a claim now that the sign is the minus to the number of crossovers in the permutation. Okay. So I'm writing down the permutation with the stipulation. And then I claim that, in fact, the sign can be computed combinatorially as how many crossovers are there and count as even or odd. And the way to see that is basically you put your lower list of numbers in this permutation as 1, 2, 3, 2k, and then you have I1, I2, I3, I2k. And this is already in the stipulation, so this is actually 1, and this is the pair that's associated with the I1 in the partition, and then this is the smallest remaining, and so on and so forth, the stipulation. And then you just imagine that how many transpositions are you going to perform to move it back to this sorted order, okay? And the parity of that is exactly the sign, of course. We're doing the inverse of this transposition, this permutation. So the sign of that is the parity of the number of the transpositions that will go. And so you think about where 2 is, and you try to move it back. So imagine that the pairs that are both inside, they are patched, then they don't contribute as even, and otherwise those crossovers will be moved by exactly 1. So when you move the thing over just to put 2 in right place, then it's exactly the number of, it's the parity of the number of crossovers of the pair I1, I2 formed by any other pairs. And then you do induction after that. Okay? So, so this is just, I was saying, if you want to move the 2 in the right place, then this is exactly the crossovers you form with the first pair with the rest. Okay. Now, the Fafian can be computed in polynomial time. There is a way to do it like the Gaussian elimination. And in fact, there is this well-known identity which says the determinant is equal to the square of the Fafian. And the fact that these things can be computed in polynomial time is important for us. Okay. Now, so far, we're thinking about a graph with edges of complex weights or just some number. But you can think about symbolically the edges having a polynomial indeterminant x. Okay? So you can have, for each edge, assign an indeterminant x whenever there's an edge. But in order to be antisymmetric, you have to assign for the edge in one way and the other with a negative sign. So this is just sort of symbolically write down the adjacency matrix as we have been doing. Let the MG denote the set of perfect matchings. And we already commented that for a particular permutation, this partition is a perfect matching if and only if all the pairs are edges. Okay. So I'm going to define the weight of a perfect matching as simply you multiply the indeterminants on the edges. Sometimes it's a little confusing if you think about these are complex numbers, and these can be already negatives, and then the weights could be negative and so on. But for now, this is why I choose to think about them as indeterminate. So don't worry about the negative part of the weights themselves. We'll have plenty of negatives to worry about in a minute because they have negative xi's all over the place later on. But right now, we're just thinking sort of straightforward a monomial, which is the weight of the perfect matching. Now let's think about an orientation of the graph, which is basically to assign one and only one direction for every edge. Okay, so you take every edge, 7, 9. You can orient from 7 to 9, or you can orient from 9 to 7. That's an orientation. For every edge you assign that, that's called an oriented graph. And for an oriented graph, let's modify this matrix in the following way. Namely, if you are ordering from, orienting from U to V, then you just put this x sub e there. Otherwise, if you opposite direction, or reversely, if you orient it from V to U, then you put a negative there in this entry of VU. Okay? Another way of thinking about this is to say that I'll modify the A to B in the following way. This A can be viewed as, where is it? That I'm sort of by default orienting from the lower to the higher. And if I were to orient in such a way that for a particular edge, the orientation was the reverse, then I put a negative sign there. But if I want to put a negative sign, I have to put a negative sign on the other side, which may already have a negative sign there. Okay, so you just flip. So that's the definition of this adjacency, anti-symmetric adjacency matrix for an oriented graph. So this is what I'm saying, that you can just think about this as modifying the A in this way. And now you can think about the Fafian of this matrix B, which is designed for the modified or the oriented graph. The Fafian for any antisymmetric matrix is well defined, so this is the Fafian. And you can think about this Fafian and think about an arbitrary term. As I mentioned, that this quantity, you can write down the pi whether or not it satisfies the stipulation or not, doesn't matter. As long as the matrix B is an antisymmetric, then you can write down the pi for any permutation that representing the partition. Okay, so now comes the definition called the sign of this perfect matching. You're given a perfect matching in the oriented graph, and you define the sign as this ratio. Remember, this is just sort of the, irregardless of the orientation, you just put the weights there. And this is the term that I just defined, which is, of course, always going to be a plus-minus sign. You can say that perhaps all of this business is about the plus-minus sign. But that's kind of making it too little, because this is where, in fact, we think is not polynomial time computable versus what is polynomial time computable separates. Okay? So determinants, Fafians, counting perfect matchings, planar graphs becomes polynomial time computable precisely because the careful assigning of the sign. And if you don't have the sign, you have the permanent. And these are typical Sharpe hard problems. Okay, so we could...
What's the denominator?
This one? This is just the product. This is the weight of the perfect matching. So we had this... just product, without worrying about. Okay. We can compute this with any permutation that satisfies, not the canonical one, because the invariance we noted about this term. Okay, that's coming sometimes convenient. So for example, we can always write down the permutation as simply the edges go from this to that. I always go from here to there. This is not, in general, going to be the canonical representation for the permutation, but I can write this way and compute its sign, and that will be exactly this sign. Okay, so now let's consider there are two perfect matchings. Okay? Suppose you have two perfect matchings. Well, what do you do whenever you have two perfect matchings? There's only one thing you should do whenever you have this is, of course, for the graduate students in the course. If you have two perfect matchings, the only thing you do, the first thing you do, is to do an XOR, right? Okay. When you do an XOR, then the set of edges of the union of the two perfect matchings gets partitioned into alternating cycles, as well as they are common edges. That would be, you can think of as cycles, and that's two. Make sense? So you take one edge of M, but not in M prime, let's say, and that vertex on the other side is perfectly matched by M prime on something. So it's a unique way to go. Okay? That must not be in M, because M is already matched. Right, so M edge here, and then you have this vertex must be matched by M prime, so there's a M prime edge. And this must not be the perfect matching edge, the blue. The perfect matching this must not be this, and therefore must be this. And therefore, now this vertex must then be matched by M prime, so there's another one. So this is M prime, and this is M. And so, of course, we're talking about finite graphs, so eventually it would have to come back, and it has to come back to this. That's the only place it can go. So whenever you're given two perfect matchings, the first operation you should think, like when you're sleepy, the first thing you do is, right, the XOR. That gives you a bunch of alternating cycles, as well as common edges, which is sitting somewhere. Okay, so that's what you do. You do the XOR. Then you have a bunch of even length cycles. It's even, right? So it's blue, green, blue. I'm not talking about red. Blue, red, blue, red, blue, red. Okay. So now I'll give a very technical definition at this point, and after the lecture you can forget about it. It's another very fundamental definition, unlike some of the others. Okay. So here's a technical definition. It says that for an oriented graph, take a cycle of even length, and we say it's evenly oriented if there's an even number of edges oriented in one direction. Pretty natural definition. Okay? It doesn't matter which direction, of course, right? Because it's even, so if you have even this way, then you have even that way. Okay, so that's called evenly oriented. Otherwise, it's called oddly oriented. It's oddly oriented even cycle. Awesome. And so now comes a lemma. I say that the sign of perfect matching M and the sign of perfect matching M in an oriented graph G is going to be the -1 to the number k, where k is the number of evenly oriented cycles, even cycles in this XOR. Okay? So that's a nifty claim. So you take the red and the blue perfect matching, you do the XOR, you get a bunch of even cycles, and then you count, because these edges are oriented, and you count how many evenly oriented cycles are there, and this identity holds. So here's a proof sketch. If it holds for one orientation, then it holds for all orientations. So this is just a little local change. If you orient one edge on the cycle a little differently, then both will change the sign, but this doesn't get changed. Sorry, if you change one edge, then one change, the other doesn't change, and this does change. I want to keep you awake and make sure that you didn't let me pass through that. Okay, and then the claim is that you can choose an orientation, and you can have it so that it's easy for us to discuss. So for every cycle, we just orient it this way. Okay, so for every cycle, we just orient it in a cyclic way. It doesn't matter which orientation. Since every orientation will, if one orientation works, then all orientation works. So you can choose the orientation you like. So now we are getting away with the orientation on given and doing a way that's convenient for us for the particular two perfect matchings, M and M prime. And now we can relabel the vertices. Again, we claim that if you after the relabeling, if this worked, then originally it worked. So it's again, this is sort of I guess a proof by invariance or something. I don't know. There has to be a name for this sort of proof technique, right? You try to push into a very standardized, canonical way, and then you say, now it's obvious. Okay? So you're going to relabel vertices. And again, if you think about it carefully, you're going to change both signs, basically. So imagine you have a permutation like this, and you're going to do another relabeling. And then you choose the M so that this is the M, and then you do this. And you compose these two, and you just get 1 to K to this. So you choose the permutation, you write it this way. Of course, generally permutation you write down 1, 2, 3, but you can write any order you like, right? So you choose the permutation this way, and then if the original M is written this way, where the oriented edges always go from I1 to I2, I3, I4, then after this relabeling, it's also going from J1 to J2 and J3 to J4. So therefore, the sign, as I told you, the sign can be computed in any particular way of writing a permutation representing it. It will be the sign of this composition of these two permutations. Okay? Now, what about this? Well, you now have an M prime, and then for the M prime, you actually have a different way of writing the permutations, right? But now you use the same relabeling permutation, writing it according to how the M prime is. You reshuffle the thing, you represent it this way, and then the product again will be the sign of this permutation for the other term. So the change of this and the change of that are both by multiplying by the parity of the permutation of this. And of course, that's a plus minus 1, so the product becomes 1. So the change is no change. Okay? So if you relabeling, it doesn't change this part. It changes this and changes this by the parity of this, both. Therefore, it doesn't change in the end. And so now we can relabel, and we'll relabel in a very convenient way. For example, in the cycle we just had, so cycle, even cycle, you just order this way. Starting with 1, let's say 1, 2, 3. Okay? And in this way, it is clear that this is identity, because the permutation is just 1, 2, 3. That's how the permutation would be. And this is a cyclic shift. So 1, 2, 3 becomes 2, 3, 4. That's how the permutation would be. For this permutation, this is 1, 2, 3 of 2, 3, 4. Right? So this is an edge, this is an edge, 2, 3 is an edge, 4, 5 is an edge, and so on. So that's going to be the parity of this, but this is an even cycle, so it's an even cycle. It's odd. That's a funny notion, right? Even cycle is odd, parity-wise. Even cycle, that's 2 is odd. Okay? And then you have a bunch of cycles, and you multiply, and that's exactly what this quantity is, because every cycle now is evenly oriented. I'm orienting this way. Everything is evenly oriented, so the number of cycles, and that's exactly number of factors. So, it's all worked out, right? It should be. See, here's another meta thing that we seem to come to appreciate in this classification program, is that in order to be polynomial time computable, something very beautiful has to just work out. Okay? So something, extremely pretty that just perfectly fits is a good sign that there's something polynomial time algorithm lurking around. So this is an example. Okay, so after this, you relabel consecutive, then it's exactly head to tail, and then you get exactly right. Okay? sign. The other sign is identity. This sign is exactly the number of even cycles, which is the number of evenly oriented cycles. Every cycle. Okay, so now I come to this definition called the Fafian orientation, which is at the heart of the Custodians or FKT argument. How much time do I have? 10, 15. Okay. So, a Fafian orientation, I'm talking about a planar graph now, a connected planar graph. An orientation of a planar graph is called Fafian orientation if along the boundary of every non-outer face, okay, so the outer face doesn't count, for every internal non-outer face, there is an odd number of clockwise oriented edges. Okay, so that's the definition of a Fafian orientation. So now we'll prove this lemma. It says that whenever I gave you a Fafian orientation, if you now look at every cycle, the cycle could bound a face or could bound several faces. Internally there are other faces. Okay, it's just a cycle. Then you look around this cycle, the number of clockwise oriented edges is of the opposite parity of the number of vertices inside. So you look at a planar graph, and then you look at a particular cycle, and here are edges inside. And then you look at the number of vertices, okay, and you count. And you say the number of clockwise oriented edges. So this edges, some going this way, some going that way. You count the number of oriented cycles in the clockwise sense. It has exactly the opposite parity of the number of vertices inside. Is that clear, the claim? Okay. So when I say inside, I don't include the number of vertices on the cycle. Okay. So let V and E be the number of vertices and edges contained inside this cycle. And let L be the number of edges on the cycle, which is also the number of vertices on the cycle. Okay? As I said, the vertices inside is strictly inside, not on the cycle. Suppose there are F faces, 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many faces are there bounded by the inside of this cycle? And let Ci be the number of clockwise oriented edges on the boundary on each of the cycles. Now, every internal edge like this contributes once in the clockwise count of one face, but the other counts 0. It counts exactly 1, contributes exactly 1 to the count of clockwise oriented edges for the internal edges if you sum over every face. But the external edges will contribute 1 only once because it's on the outside. There's only one face that's inside. So everyone contributes really 1. Now, take the number of faces. Since I said it's odd, every face has an odd number of oriented cycles. It's odd, so this is 0. This is 1 mod 2 every one of them. So F is equal to the congruent. Is congruent to the sum of the count of the number of clockwise oriented edges per each face, mod 2. Okay? This is just saying F is congruent to sum of 1 mod 2. Every Ci is 1 mod 2. Now, of course, there's the Euler's formula. This is where the planarity comes, right? The number of vertices, including the points on the cycle, is V plus L. The number of edges is E plus L. the number of faces is f plus 1 because there's one external face outside of this cycle. Forget about these edges altogether. Just think about this and the external face. Okay? And that quantity has to be 2. And doing some arithmetic, you get this quantity. So this is the quantity we had. Okay? And we had this sum to be congruent to f. And this thing says that every edge inside and as well as on the surface clockwise edges contributes exactly 1 to this count. This is the number of edges inside. It contributes exactly 1 whenever you sum for all the internal faces the clockwise edges. Once in the one face for which it's clockwise and the other it doesn't contribute. And the the C is the number of clockwise edges on the outer surface, outer cycle. That contributes also 1. Okay, so you get this quantity, this equal to that, and by the Euler get this, and you get this quantity. So it just falls out. Okay, so this says the number of vertices strictly inside versus the number of clockwise oriented edges on the cycle that you picked is of the opposite parity. What? Okay. And so now the key point is to say that if you have a Fafian orientation, then these two signs for any two perfect matchings will have the same sign. Okay? So this is all this game is about, that you eventually get to this point. That's the whole thing. So you're given two perfect matchings. Because it's a perfect matching in a planar graph, the vertices inside cannot match outside because this is in a cycle that's made of the alternating. You take two perfect matching, you do the XOR, remember? Okay? So when you do the XOR, then the vertices inside cannot be matched outside. So the number of vertices inside must be even. So the number of clockwise oriented edges must be odd. So therefore, it's not an even oriented cycle. That definition, the even number of oriented clockwise things. So therefore, the sign is going to be 1. They're all the same. Okay. So with the same sign, we are now ready to link this directly with perfect matchings. As we have been talking about, the Fafian always has this with up to a sign connection with perfect matchings. And now we are going to say that they are really the same if you have the Fafian orientation. Really the same up to a global factor of possibly a -1. But they are all the same sign in the Fafian. So let's define the perfect matching polynomial. This is like what the permanent would have said. Right? The sum of all things of the product without any additional artificial sign on the permutation. And if you assign these indeterminants to be 1, then this will count the number of perfect matchings in the graph. And now here's the theorem of Castellan. That says that for any connected planar graph, you can assign a Fafian orientation, and once you can, I'll come to that later, this Fafian orientation can be computed in polynomial time, in fact, faster. And using that, you can compute this number of perfect matchings by Fafian, basically. Okay. Now, intuitively, if you have a planar graph and you want to make sure that on every face you have the right orientation, you have the odd number of clockwise oriented edges, then you just sort of grow, right? You just assign it. Okay, odd, and then look at here, this is already assigned, so you do something on these 3 edges so that it's right, and here and here. You can keep grow, and then it seems to be fine, right? Okay? This is not quite right, because sometimes when you just did this growing, at some point you may come to a sort of contradiction. I mean, there's no guarantee of consistency if you just naively do that. Okay? But this idea is basically right. So what you do is you take the connected planar graph. You can compute its planar embedding, Hopcroft-Tarjan. And if it's a tree, then any orientation works because there's no cycle, there's no requirement on the cycle. If not a cycle, then there must be an edge that's on a cycle. If not a tree, there must be an edge on the cycle. And you just traverse the external edges. If an edge is not on a cycle, it must be a cut edge. And you can break them. And then inductively over here and over there, there must be an edge that's on a cycle, and then you paste back that's an edge on a cycle. So you can always easily find an edge that is on a face, on the face of an embedding, an internal face, not an external face. Okay? And now you take this edge away, and that either disconnects it, which then it's easy, or it just breaks one particular face, like this edge is being broken out. And then you inductively do what you need to do for the orientation so that every face has a Fafian orientation. And then you append this edge's orientation one way or the other to make this face right. Remember, the Fafian orientation does not require anything on the outer face. Okay, so you don't need to worry about what the outer face will happen. So this gives you the Fafian orientation. Is that clear? It's very simple, right? Okay, so you can get a Fafian orientation, and once you have the Fafian orientation, you write down the skew symmetric matrix for the orientation I gave you for the Fafian orientation for the graph. And then the Fafian will either be the perfect matching or the negative of the perfect matching as a polynomial now. Because every term in the Fafian for each perfect matching has exactly the same sign. They are both positive or negative relative to the weight of the perfect matching. Okay? So that was the thing. Now there is this sort of issue. If you write down this whole thing and then you still want to compute the perfect matching, which one is it? Is it plus or minus? You compute the Fafian. Well, one quick and easy way is to say, well, I just set all the weight to be 1. If your original weight may not be all 1, I don't care. Assign all the 1 and compute the Fafian for the particular Fafian orientation I just made, and I get a value. And this value is either positive or negative, or it could be 0. 0 would be there's no perfect matching, right? Okay, and since it's all 1, the perfect matching part must be, the number of perfect matching must be non-negative, so you know which one it is. And then you go back to the original weight and recompute. That's one way. I think there are other ways. This is not the same as the sign issue when you have the Fafian square equal to determinant. You compute the determinant, then you still have the issue of the Fafian being plus or minus. Okay, but actually, you could compress the two things here together by computing the determinant, and then you know the plus or minus sign is the right one. If it has a bunch of connected components, then you just compute component-wise. That's the perfect match. So that gives you the polynomial time algorithm. Okay? Maybe 5 more minutes to... I'm trying to be slow going, and hope you sort of can follow everything. I really want to make it elementary here. Okay? Now, with the Fafian orientation and Castellian's algorithm in hand, then we can define what's called the match gates. So what is a match gate? Well, it's basically a undirected weighted planar graph with some vertices outside as designated as external vertices or edges. You can have dangling edges coming. So you have something like, you have here, 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 the 3 vertices that are external. Okay? And the match gates are to be considered as whether this edge and this edge and this edge are being externally matched or not. And once you externally match this and not that, then you would match this by removing this together with incident edges. And you say, what's the perfect matching value inside? and that will become one entry of the match gates. So given the match gates, like for example, 3 external nodes, it will define a vector or a tensor of, I think in terms of entries, there will be 8 values. And they correspond to particular patterns of external vertices being externally matched or not. Given that particular matching consideration, what's the internal perfect matching value? So that's the match gates. So formally speaking, you take a pattern of 0, 1s, and you remove the vertices that have a 1 in the graph. You compute its perfect matching value. Okay, so that gives you a bunch of values, and that assembles into a tensor or a vector. As being perfect matchings, of course, it is the case that only half of the entries can be non-zero at most, because by parity, what remains has to be even in order to have a non-zero perfect matching value. So if G has an odd number of vertices, then you must remove odd number of vertices externally to make it possible to have a perfect matching inside. If you remove even number of vertices, what remains will still be odd, and that will be 0. The value will be 0. Okay. So the perfect matching can be viewed as a Holland problem, and you can assign the exact one function at every vertex and pick an edge to be in or out. Okay? And now here's the definition of what's called a Holland sum. You're given a set of constraint functions, for example, exact one function, or at most one function. If it's at most one function, that will be not necessarily perfect matchings. And you sum over all possible edge assignments of this product, which in the 0, 1 case will be either yes or no. In general, will be some sort of weight. And this quantity will, is in the perfect matching case, will exact one function here will count the number of perfect matchings. So let's look at, maybe I'll stop here and I'll pick up the next one.
Yeah.
Okay, so
I think it's not a good idea to rush through
yeah,
this stuff.
right.
It's fairly important.
Any questions? Not too many. Now you all understood. Yeah. What I am talking about here, as well as what comes next time, will all pretty much in the book that I'm writing that you can take a look. And there are plenty of papers on the website that will be more specific.
So, the FKT has a kind of sort of topological field.
I know if that's...
Would you repeat the question? Can't hear a thing.
FKT seems to have a topological flavor.
So, I mean, is there any extension of it to sort of simplicial complexes?
Fixed genus, you can do it, but general simplicial complex.
So the Fafi orientation is supposed to be like a spin structure, if you think about it that way.
Yeah.
Then you need some notion of spin structure for a general simplicial complex.
Just asking if anybody ever considered this question.
Well, it needs to look like a manifold, right?
Well, I think so. There are some work, Ming-Chi and Radu, and they have done some extensions on higher genus and certain violations of planarity, what you can do. I think generally, say for genus, for example, you can have a polynomial time algorithm with G on the exponent. So you have n to the order G, polynomial time algorithm. But if you want to use so I didn't quite get to the use of the match gates. If you want to use match gates in general as non-planar, then to substitute into a general CSP problem, for example, then there's no guarantee that you can maintain the genus to be bounded because they're going to replicate in an unbounded fashion. And once the genus is unbounded, then it's Schottky hard. So dichotomy theorem says you can't, unless you think Schottky could be. So that's
Any more questions? Is it thank Jin-Yi and go to break?